Hello. Well, I'd just like to finish off our analysis of the recognizing objects in range data with a little bit of discussion. The first thing I'd sort of like to talk about is our choice of the primitives. We used planes as the primitives to do the matching, and generally the reason for that is they're quite reliably extracted from the range data. But there are alternatives, and one of the alternatives is to use edges. When you look at range data, there's actually sort of three different kinds of edges that you could find. Okay, first is what you might call a depth, a blade edge, where you have effectively a discontinuity in the depth as you look past one surface to see another surface in the background. If you look at the range data, you'll actually find a big step change in the depth values. It'll go from sort of closer to further away. And you can build edge detectors that will detect that kind of blade edge. And that gives you some useful information about the position of surfaces and the edges of the objects that may not be obvious from intensity data. Another kind of edge that one could get is edges that are related to discontinuities in the surface orientation. This is what's called a fold edge. So if you were looking at a block that had two planar surfaces meeting something like that, if you were looking like this, you would see that there's a change in the surface orientation, the surface normal, off of these two edges at this particular position. That's what's called a fold edge, and we saw that we had lots of those on the kind of polyhedral blocks that we're working with. And they're quite common in built environments because that's the way humans build things. You got walls that are perpendicular to each other and perpendicular to the floor and ceiling. You've got filing cabinets, you've got boxes, you've got desks. All of these consist of planar edges that sort of meet at 90 degrees. And so the fold edges are a very common kind of feature that you can see particularly in the built environment. If you're looking at objects like faces or golf clubs or something like that, bottles and containers, you might also find a third kind of edge. And that's where the curvature, boundaries between regions on the surface where the curvature properties change. For example, where it goes from being a convex surface to being a concave type surface. And you can find edges between this. And once you have that range data, then it becomes easier to actually find those edges, unlike we're working with intensity data where it's virtually impossible to sort of see those kinds of boundaries. Well, in the case of sort of using features for recognition, the blade edges and the fold edges are often quite useful for doing recognition. And you could use them in much the same sort of way as that we used in the two-dimensional case for doing object recognition, or also in the three-dimensional stereo case, which is a different lecture set. But on the other hand, the planar surfaces that we extracted are really quite reliably extractable because we consist of a large number of 3D points, and we can sort of cope with small amounts of noise and still get an accurate estimate of the planar surface. But this is not so true really of estimating the blade edges and the fold edges. The range sensors don't work as well when you get two edges because typically the sensing mechanism will see a little bit of both the foreground or the background, or in the case of the fold edges, it will see a little bit of both of the surfaces, and it'll give you an estimate of a point which isn't quite either the foreground or the background or either of the folds. And that creates a little bit of a problem right there for estimating the precise position of these kinds of edges. But usually it's not too bad. It's just, I think, in my opinion, maybe just not quite as accurately estimatable as the planar surfaces. Well, range sensors are now commonly available. With the Kinect sensor, you can get them everywhere. Anyone who builds a mobile robot can easily get a range sensor to go on top of their mobile as well too. Sometimes they're Kinect, sometimes they're other sensors. You can get a commercial sensor that's pretty accurate for only 1,000 pounds. You don't need the 50,000 pound type sensors that I was talking about previously. That was from quite a number of years ago, and now the similar technology is much cheaper, maybe not quite as accurate as that, but certainly more accessible. And we even built a sensor that I think used altogether maybe 20 pounds worth of components and a little bit of software, whatever, for not very high quality, but a very low cost type sensor. As I've said, the accuracy can be really quite amazing for this, sort of these commercial sensors. We can really get down to very fine details. That's small enough that if you had a polished piece of metal and you touched it, you could measure the fingerprints on that metal. The Kinect sensor is not nearly so accurate, but it's also a very cheap sensor, and the accuracy could be on the order of a few millimeters to a few centimeters, depending on the distance of the target from the sensor. As we saw, the range data is really quite unambiguous, and this allows us to interpret it directly, and we can fit surfaces to it, and we can find edges, we can find particular shapes, we can make measurements. All of these things are done because we have more or less accurate measurements of where the surface really is, rather than just kind of secondary characteristics that we're measuring based on just the light that's reflected from the surface. We looked at one particular region growing type method that's useful for finding the planar patches in the data, and one could extend it also for finding cylindrical and spherical type surfaces as well quite easily. There are different ways that one could actually find these patches. Not all of them are based on region growing. Some of them are based on finding these kinds of blade and fold edges that I was talking about previously. These algorithms tend to be so have a bit of a trade-off between sort of accuracy and speed. So the fast algorithms also tend to have an opportunity to make errors a bit more easily. The region growing algorithms tend to be a bit slower but are more accurate. So it's a kind of trade-off that you may want to choose to make. We just looked at data that was in a point cloud. If you have the ability to actually acquire a range image, one could easily store all the data in a three-dimensional array where you have the horizontal and vertical rows and columns of the image, and then you store it in 3 dimensions with the x, y, z coordinates of the actual point. And this could make your algorithms be more efficient and simpler as well too. The techniques of using range data are not suitable for all types of problems. Some people use them for face recognition, but so far that hasn't taken off very much. Mostly people still tend to use intensity data for face recognition and verification. But if you're working in a robot navigation type context, then having the range data as well as the color data can be very useful for finding obstacles and finding surfaces that you can drive your vehicle on. And the data is also very useful in an industrial context, because there you're often concerned about the shapes of objects or the position of features in the objects, and the range data can help you quite a bit with finding those accurately. Well, we really had a very simple sort of task here. That was the recognizing just basically a block in a set of range data. And what I think is quite interesting is, although the task was really quite simple, this gave us an opportunity to introduce quite a lot of new types of technologies and ideas in the kind of computer vision sort of field. And that's what we've sort of summarized here. We've looked at ways of both acquiring and representing three-dimensional data and depth data that we hadn't seen previously. Previously, we only looked at intensity data. We looked at some of the different sensor technologies that could actually give us that kind of data, the triangulation sensors or the time-of-flight sensors. We looked at a way for extracting some features from that range data, and the planar fitting of the 3D data is a perfect example of it. It's much like fitting a least squares fit of a line through a set of edge data that we could also look at. We looked at a kind of region growing algorithm. We haven't seen this one so far. We looked at ways to extend our two-dimensional coordinate systems into three-dimensional coordinate systems, and looked at how to do some of the transformations and representations using those. We extended our two-dimensional wireframe representation into a three-dimensional wireframe. And similarly, we extended our two-dimensional least squares pose estimation algorithms into three-dimensional pose estimation algorithms. So there's quite a lot of things that we've covered right here in this system. Thank you very much.